Yes friends, welcome back to the class chemistry. Now we are continuing the 9th class states of matter, exercise 3, stage 1, stage 2 including advanced level. Yes friends, in the previous part I discussed the first 10 or 11 questions that given in the exercise 3 stage 1. Based on the previous two videos, you can solve majority of the questions. But there are 3 or 4 different types of questions. I will show you how to solve it. Take the question number 12th. Question number 12th. Yes. A sample of water gas contains 42% by volume of fraction of by volume. Yes. A sample of water gas contains 42% by volume of fraction volume, that's all. If the total pressure is 760 millimeters, calculate the partial pressure of carbon monoxide. Here it is somewhat different model. Actually the partial pressure of a gas is equal to total pressure of the gas mixture into mole fraction, we know that. Mole fraction is the mole fraction of a gas is equal mole number of that particular gas present in the mixture by total number of moles of all the gases. But here the mole numbers are not given. Even the weights of gas are not given. If the weights of gas are known, we can calculate the mole number. The weights are not given. The mole numbers are not given. But what was given in the problem? It contains 42% of volume of fraction of carbon monoxide. Okay. If the total pressure is 760. Yes. A gas mixture contains, of course, it is water gas. A water gas contains 42% of carbon monoxide by volume. Remember, this is the most important one. Is it by volume or by mass? In our previous questions, the mass ratio is given. The methane and oxygen are taken in 1:4 mass ratio. Here, the volume percentage is given 42%. That means, so the water gas contains 42% by volume. Here the principle is PV is equal to nRT at constant pressure and constant temperature. V proportional to N, because pressure is constant, temperature is constant, R is already a constant. Pressure is constant, temperature is constant. At constant temperature and pressure, P is constant, T is constant, and we know that the R is also a constant. That means V proportional to N. Friends, instead of mole number, you may take the volume, because mole number is directly proportional to volume. Therefore, from the data given in the problem, the water gas contains 42% of carbon monoxide but by volume. That means number of moles of carbon dioxide may be taken as number of moles of carbon monoxide is taken as 42 because it is percent. Therefore, that means the total volume of the gas mixture, here the gas mixture is of course water gas. So, total volume is 100. In that, the volume of carbon monoxide is 42. That is the meaning of 42% of carbon monoxide by volume. That is the concept behind it. Therefore, instead of number of moles, you may take the volume. Therefore, the partial pressure of carbon monoxide is equal to the total pressure of the gas mixture into mole fraction of the carbon monoxide. Mole fraction of carbon monoxide means number of moles of carbon monoxide by total number of moles. Total number of moles. Total number of moles. S. What I have explained in the previous, instead of number of moles, you may take volume. Therefore, the partial pressure of carbon monoxide is equal to the total pressure is given as the total pressure is given as 760. Therefore, the total pressure is 760 into, instead of number of moles of carbon monoxide, we may take the volume percentage of carbon monoxide. That is 42 by total mole number. It is 42%. Ante in 100 volumes, the 42 volumes of carbon monoxide is there. Therefore, what is the total volume? Total volume is 100. Therefore, partial pressure of carbon monoxide is equal total pressure. In the probability was given that the total pressure of the water gas is 760 into mole fraction of carbon monoxide. That means number of moles of carbon monoxide by total number of moles. The number of moles of carbon monoxide is nothing but the volume of carbon monoxide by total volume. Now, if you calculate it, it gives the answer. Just calculate it. That's all. So, it is somewhat different problem. Instead of number of moles, the volume fraction is given or the volume percentage is given. So, instead of number of moles, we may take the volume because the volume is directly proportional to number of moles at constant pressure and temperature. That's all. That is this one. Ends. Coming to the next question. The remaining questions are: a vessel contains, question number 13, equal weights of methane and oxygen at 25 degrees. The partial pressure of oxygen in the total pressure. Equal weights of methane and oxygen. Already we have discussed such model. Then question number 14. Equal weights of ethane and hydrogen are mixed in empty container at 25 degrees centigrade. The fraction of total pressure exerted by hydrogen. Here also the equal weights or the equal mass of methane and hydrogen are taken. The same model. Question number 15. A mixture of carbon monoxide and carbon dioxide is found to have density of 1.7 grams per liter at STP. The mole fraction of carbon dioxide is, friends, it is entirely different model. It is entirely different model. There is another principle related to this mole fraction, that is the concept of density. Again read the problem. a mixture of carbon monoxide and carbon dioxide is found to have density of 1.7 grams per liter. The density of the gas mixture is 1.7 grams per liter at STP. At STP. Calculate the mole fraction. We have to calculate the mole fraction. The density of the gas mixture is given. It's a different model. Now I will show how to solve it. Here the density is 1.7 grams per liter. It is a mixture of carbon monoxide and carbon dioxide. Its density is 1.7 grams per liter at STP. It is a condition. Calculate the mole fraction. We have to calculate the mole fraction of either CO or CO2. Mole fraction of CO is equal to number of moles of CO by total mole number, and number of moles of CO plus number of moles of CO2. But number of moles are not given. Even the weight of carbon monoxide and carbon dioxide is not given. So without knowing the either weight of the gases or number of moles of gases, how can we calculate the mole fraction? Here, the density is given. The density is equal to mass by volume. At STP, the density of a gas is equal to its gram molecular weight. Its gram molecular weight by gram molar volume. Friends, you know what is density? Density is the ratio of mass and volume. But in the case of an ideal gas at STP, the density of an ideal gas at STP is the molecular weight by gram molar volume, not gram molecular weight, gram molar volume. Molecular weight by gram molar volume. Gram molar volume means the volume occupied by a 1 mole of gas at STP. You know that the gram molar volume is 22.4 liters. Therefore, the density is given as 1.7 grams per liter is equal to the molecular weight of the gas mixture by gram molar volume is 22.4. Therefore, the molecular weight of the gas mixture is 1.7 into 22.4. 1.7 into 22.4 means, calculate that value. 1.7 into 22.4, that is equal to 38.08. It is the step 1. What is it? The molecular weight of the gas mixture. It is a gas mixture. So this molecular weight is taken as the average molecular weight of this gas mixture containing CO and CO2. Yes. From this, we can calculate the number of moles. Here there is another formula, another principle. Yes, here the average molecular weight of a mixture It is average because it is not the molecular weight of a single gas, it is a mixture. The average molecular weight of a gas mixture is equal to, the formula is the molecular weight of the first gas into its percentage plus the molecular weight of second gas into its percentage. Let us take that it is X%, it is Y% by 100. We can calculate the average molecular weight of isotopes by using the same formula. Therefore, let us take that in the gas CO plus CO2, if X milliliters of carbon monoxide is present, let us assume, then the carbon dioxide volume is 100 minus X milliliters. Therefore, the average molecular weight of the gas just now we calculated 38.08 is equal to, the first gas is carbon monoxide, its molecular weight is 28, carbon atomic weight 12, oxygen 16, 28 into X milliliters of carbon monoxide is taken plus M2. M2 is the second gas, carbon dioxide. Its molecular weight is 44 into its volume is 100 minus X by 100. Friends, there are two steps. Because density is given, density of a gas mixture is given, we calculate the average molecular weight of the gas mixture. Average molecular weight is this one. Density is molecular weight by gram molar volume. Gram molar volume is 22.4. Therefore, the average molecular weight of the gas mixture is equal to density into 22.4, 38. So here, the average molecular weight of a mixture is equal to the molecular weight of the first gas into its volume percentage plus molecular weight of the second gas into its volume percentage by 100. Substitute the values. The average molecular weight of the gas mixture just now we calculated 38.08 is equal to the molecular weight of first gas. Here the first gas is carbon monoxide 28. Let us take that volume is X% plus the molecular weight of second gas is carbon dioxide 44 into its volume is 100 minus X by 100. Calculate this. If you calculate this, 38.08 is equal to 28X plus 4400 minus 44X by 100, or by cross multiplication 3808 is equal to minus 16x plus 4400. Calculate the x value. Thus x value is 4400 minus 3808 by 16. Calculate that value. That value that is 4400 minus 3808, that's divided by 16, so that is 37. That is 37. What is 37? The mole fraction of carbon monoxide is 37. Let us see what are the options given. A mixture of carbon monoxide, question 15, and carbon dioxide is found to have density 1.7 grams at STP. The mole fraction of carbon monoxide is 0.37. 0.37. Here 37. 37 is for 100. So fraction, mole fraction means for 1. That is 0.37 is the answer. Okay, somewhat different model. There are two different concepts are introduced here. It's advanced level, no doubt. Here, the density is mass by volume, but we should know that the density of a gas at STP is equal to its molecular weight by gram molar volume. Gram molar volume is 22.4. But it is not a pure gas, it is a mixture of gas. In the case of mixture of gas, the density of the gas is equal to average molecular weight of the mixture of gas by gram molar volume 22.4. Therefore, average molecular weight of the gas mixture is equal to the density of the gas mixture into 22.4. That gives the average molecular weight of that gas mixture. Friends, remember, here the average molecular weight of the carbon monoxide and carbon dioxide in the given gas mixture is 38.08. You know that the molecular weight of carbon monoxide is 28 and the molecular weight of carbon monoxide is 44. In that mixture, the average molecular weight is 38.8. Are you following? You know that the carbon monoxide molecular weight is 28 and the molecular weight of carbon dioxide is 44. But the average molecular weight of the gas mixture is 28.08. That means in the mixture some percentage of X, and that means carbon monoxide, and some percentage of carbon dioxide is given. Based on that average molecular weight, you can calculate the percentage of carbon monoxide and the percentage of carbon dioxide present in the mixture. So the formula is the average molecular weight of the mixture is equal to the molecular weight of the first gas into its percentage of the gas present in the mixture, plus the molecular weight of the second gas into its percentage by 100, because it is per percent, so that the total is 100. Therefore, average molecular weight of gas just now we calculated. We know the molecular weight of the first gas, that is carbon monoxide. We know the molecular weight of second gas, 44. Let us take that the percentage of carbon monoxide is X in the mixture. Then the percentage of carbon dioxide must be 100 minus 1 X. If you substitute, you will get the answer. What a beautiful question, friends. There are two depth concepts. Based on the same formula, we can calculate the average molecular weight of isotopes. Oxygen, the oxygen atomic weight is 16 and also 17 and also 18. Oxygen 16 isotope, 17 isotope, 18 isotopes are there. The natural oxygen contains nearly 99% of oxygen 16 isotope, 0.34% of oxygen 17 isotope, and remaining oxygen 18 isotope. Therefore, the average molecular weight of oxygen, if you calculate that, it gives 16 point something like that. So the average molecular weight of isotopes can also be calculated by using the same formula. That's all. Okay, coming to the next one. Yes, the next question. 16th question. Equal weights of methane and hydrogen are mixed together in empty vessel at 25 degrees. Calculate the fraction of total pressure exerted by methane, the routine model. And come to the question number 17. It is somewhat difficult question, not difficult. It is not difficult, somewhat different question. Two gases A and B having the mole ratio of 3:5 in a container. Here the mole ratio is given. Two gases A and B are in the mole ratio of 3:5 in the container. That means 3 moles of A and 5 moles of B are present in the mixture. That is the meaning of 3:5 molar ratio. And exert a pressure of 8 atmospheres. That means the total pressure of the gas mixture A and B in their mole ratio is 8. If A is removed, if A is totally removed from the container, what will be the pressure of B? If A is completely removed from the container, the pressure of B is nothing but its partial pressure. Is it not? In the gas mixture A and B are there. If A is completely removed, then only B remains in the vessel. So, if only B is present in the vessel, the pressure exerted by the B is called the partial pressure of B. Therefore, a mixture A and B are present in the mixture. A and B are present in the mixture. Their mole ratio is 3:5. A is present in 3 moles and B is present in 5, or their mole ratio is 3:5. The total pressure of the gas mixture is 8 atmospheres. If A is completely removed from the container, then B is there. So what is asked in the question? The partial pressure of B. The partial pressure of B is the total pressure into mole fraction of B. Mole fraction of B means mole number of B by total mole number. Total mole number means number of moles of A and number of moles of B. Therefore, the partial pressure of B is equal, the total pressure is given as 8 atmospheres into mole fraction of B. Number of moles of B is 5 by total mole number 3 plus 5, 8. Therefore, the partial pressure of B is equal to 5 atmospheres. If A is removed, completely removed from the container, then only B remains in the vessel. So, if the only B gas is present in the vessel, then the pressure exerted by the B is called its partial pressure. So, its partial pressure is 5 atmosphere. Let us see the answers. If two gases are AB, what would be the pressure of B only? Temperature remaining constant. Option 1 atmosphere, 2 atmosphere, 4 atmospheres, 5 atmospheres. The answer is 5. Then, coming to the next one, the pressure of a mixture of 4 grams of oxygen, 2 grams of hydrogen confined in a bulk of 1 liter and 0 degree centigrade. Very simple. The pressure is equal to number of moles into RT by V. Number of moles, 2 gases are there, 4 grams of oxygen, 2 grams of hydrogen. Calculate the number of moles of oxygen plus number of moles of hydrogen into R value known, T 0 degrees by V, 1 liter. So, if the total volume of gas is 20 liters, in which 2 grams of hydrogen, 4 grams of helium are present, find the partial pressure, partial volume of hydrogen. As friends, question number 19. Instead of partial pressures, partial volume is asked here. Instead of total pressure, total volume is given. Total volume is 20 liters. In which 2 grams of hydrogen, 4 grams of helium are present. Find the partial volume of hydrogen. Instead of partial pressure, the partial volumes are given. Yes. The total volume of a gas mixture 20 liters. The first one. Here in that 3 gases are there. What are the gases present in it? 2 grams of hydrogen, 4 grams of helium. 2 grams of hydrogen and 4 grams of helium. 2 grams of hydrogen and 4 grams of helium. The total volume is 20 liters. 2 grams of hydrogen means number of moles of hydrogen, weight by molecular weight. Molecular weight of hydrogen is 2. So, number of moles of hydrogen is 1. And 4 grams of helium, number of moles of helium is equal, weight of helium 4, by its molecular weight of helium is 4. So, number of moles of helium is also 1. Therefore, the total number of moles of hydrogen and helium is 1 plus 1, that is equal to. Here, the total volume is 20 liters, in which 1 mole of hydrogen and 1 mole of helium are given. Friends, you know that PV is equal to nRT, or V is equal to N into RT by P. At a constant temperature and pressure, RT by P is constant. Therefore, V proportional to N. Therefore, 1 mole of hydrogen and 1 mole of helium. 1 mole of hydrogen and 1 mole of helium. Total 2 moles. 2 moles of that gas contains 20 liters. Therefore, the partial volume of any one gas, either hydrogen or helium, it has only 1 mole. If total 2 moles of gas occupies 20 liters, 1 mole of a gas occupies 10 liters. So the answer is 10 liters. Here, or you may apply the formula. What is that formula? The formula is similar to the partial pressures. The total pressure of a gas mixture is equal to partial pressure of the first gas plus partial pressure of the second gas. Like that, the total volume of a gas mixture is equal to the volume of the first gas, the partial volume of the first gas plus the partial volume of the second gas. It is a Dalton's law. It is called Amagat law. Amagat law. In our exercise, another question is given. There is a key mistake. So, the total pressure of a gas mixture at constant temperature is the sum of the partial pressures of all the gases present in the mixture. It is a Dalton's law. Like that, the total volume of a gas mixture at constant pressure and temperature is the sum of the partial volumes of all the gases present in it. So, the total volume is equal to the partial volume of the first gas plus the partial volume of the second gas. The total volume is 20 liters. The partial volume of first gas is nothing but the same, the volume of that particular gas by total volume, or the volume of the partial volume of the second gas, the volume of the second gas by total volume. Here it is one volume, it is one volume. Total 2 volumes is equal to 20 liters. So, 1 volume is 10 liters. Like that. It is somewhat different model, not a different model. Similar to the Dalton's law, there is another law called Amagat law, which is the total volume of a gas mixture at constant temperature and pressure is equal to the partial volumes of all the gases present in the mixture. It is Dalton's law, it is Amagat law. That is a one. So, that is question number 19. And the partial pressure of 2 gases, 2 atmospheres and 4 atmospheres, what will be the total pressure of the, what will be the total pressure? A direct question. In the mixture there are 2 gases. The partial pressure of the first gas is 2 atmospheres. The partial pressure of the second gas is 4 atmospheres. What will be the total pressure? Total pressure is equal partial pressure of first gas plus partial pressure of second gas. That's all. Then come to the stage 2. The first question. The box is divided into 2 equal parts A and B having the gases X and Y respectively. A box is divided into 2 equal parts A and B having 2 gas X and Y respectively. If the 2 parts have equal pressures 250 millimeters of mercury, the pressure after removing the portion will be. Read the question again and try to understand the meaning what is given. A box divided into 2 equal parts A and B. The part A filled with X gas and the part B filled with Y gas. These 2 parts are equal in volume, 2 equal parts, equal in volume. And the 2 parts have equal pressures, 250, 250. If the middle portion is removed, what will be the pressure? Here, A box is taken. That box is divided into two equal compartments, A and B. Let's assume that it is divided into two equal compartments. That means the volume of the first portion is equal to the volume of the second portion. The first portion filled with a gas, that is X, and the second portion is filled with a gas, is Y. The gas X is present in the first compartment with a pressure of 250 millimeters. And the second gas Y is also present in the B compartment with the same pressure, 250 millimeters. What will happen if the partition is removed? What will happen if the middle partition is removed? Before, two volumes are equal, two pressures are equal. What will happen if the partition is removed? Then the two gases will mix together. Then before, it is P1 V1. You know that the product of PV is constant. Here it is P2 V2. Here the P1 is equal to P2, V1 is equal to V2, P1 V1 is equal to P2 V2. If you remove it, again here the first is 250, first is 250, total first is 500, and total volume is V1 plus V2. If the volume is taken as 1, 1 plus 1, 2. Therefore, the volume becomes V1 plus V2. If the volume of each one taken as 1 liter, that is 2. The pressure is 250 plus 250. 250 plus 250. That's 500. Therefore, PV is constant. Ante volume double aindi and pressure is also double. So, pressure and volume both are doubled. P is equal to N RT by V. The volume is doubled and the pressure is also doubled. Volume is doubled, the pressure is doubled. Therefore, the value of the ratio becomes constant. That means the total pressure is the constant. Here, the two portions equal volumes, two gases are also present at equal pressures. Therefore, P1 V1, same P2 V2. If it is removed, then what will happen? The total volume is now V1 plus V2. The total pressure is here 250, 250. So, P is equal to 10 RT by V. The pressure is doubled, 250 plus 250. The volume is also doubled. So, again it cancelled. The P is constant. That is this one. Coming to the another question. A mixture contains 16 grams of oxygen, 28 grams of nitrogen, 80 grams of methane. Total pressure of the mixture is 740. What is the partial pressure of nitrogen? It is a very common model. Equal molecules of nitrogen and oxygen are kept in a closed container at a pressure P. If nitrogen is removed from the system, what will be the pressure of container? Here friends, in our previous problems, equal masses of methane and oxygen are given. Equal masses or equal weights. Here, equal molecules of nitrogen and oxygen. Number of molecules are equal. That means number of moles are equal. Number of molecules are equal because number of molecules is equal to number of moles into Avogadro's number. If the number of molecules are equal, because Avogadro constant is the constant, number of moles are also equal. That means equal number of molecules of, that is the what is given in the paper. Equal molecules of nitrogen and oxygen are kept in a pressure, kept in a closed container at a pressure of P. Equal number of molecules means equal number of moles are present in the container. If nitrogen is removed from the system, and for example, equal number of molecules means equal number of moles. Let us take that 1 mole of nitrogen and 1 mole of oxygen. Total 2 moles of gas is there, then the first is P. If nitrogen is completely removed, that means half of the number of moles of nitrogen is removed, then the number of moles becomes half. Number of moles becomes half means pressure becomes half. Therefore, the pressure will be P by 2. Here, pressure is equal to L RT by P. So here, N means number of moles. Number of moles of nitrogen plus another gas which is given, oxygen I think. If nitrogen is removed, that means half of the moles are removed. So N becomes half, then P becomes half. So the answer is P by 2. Then coming to the other problem. 50 grams of nitrogen, 96 grams of oxygen are mixed isothermally at a pressure 10. The partial pressure of oxygen and nitrogen. It's very simple. A and B are the ideal gases. The molecular weight of A and B are in the 1:4 ratios. The pressure of a gas mixture containing equal weights of A and B. Yes, friends, in our previous problems, equal mass are taken. But here, the molecular weight ratio of the two gases are given 1:4, but they are taken in equal masses. Then, what will be the partial pressure of B in the mixture? The total pressure is given as P. Yes, it's very simple. A and B, the molecular weight ratio is 1:4. A and B, the molecular weight of A is 1 and the molecular weight of B is 4. Equal weights are taken. Let us take that 1 gram and weight is 1 gram. The total pressure is P. Now, the partial pressure of A or the partial pressure of B. Here, molecular weight ratio is 1:4. Therefore, the number of moles of A is equal. Because equal weights are taken, let's take that 1 gram of A is taken. By its molecular weight is 1. Number of moles of B, weight is 1 gram because equal masses. But its molecular weight is 4 because their molecular weights are in the ratio of 1:4. So here the molecular weight of A is taken as 1. Therefore, the molecular weight of B is 4. Therefore, the partial pressure of A is equal to total pressure into mole fraction of mole number of A by total mole number. Total mole number means 1 plus 0.25, 1.25. So 1.25 means that's partial pressure of A is equal to P by 1.25. Thus, calculate that value. Let's see what are the options given in that. 1:4. The partial pressure is given as P by 5, P by 2, P by 2.5, 3P by 4. Calculate it, you will get the answer. Then, here which of the following gas in a mixture shows the highest partial pressure? Which of the following gas in a mixture shows a highest partial pressure? Partial pressure is equal number of moles into RT by V. So the gas whose number of moles are more, it exerts higher partial pressure. The partial pressure of a gas is equal number of moles of that gas into RT by V. If there are 3 gases, the partial pressure of gas 1 is equal its number of moles into RT by V. The partial pressure of gas 2 is equal its number of moles into RT by V. Like that, the partial pressure of gas 3 is equal its number of moles into RT by V. So, among these 3, whose partial pressure is more? Because temperature and volumes are constant, R is already universal gas constant, the gas whose mole number is more, its partial pressure will be also more. So, in our problem, which of the following gas in a mixture shows highest partial pressure? Ante the gas which has the highest number of moles, it exerts highest partial pressure. 1 gram of hydrogen means 0.5 moles. 7 grams of nitrogen means nitrogen molecular weight is 28. 7 grams of nitrogen means 1 by 28. So it is 1 by 4 moles. It is 1 by 2 mole, it is 1 by 4 mole. 4 grams of helium is 1 mole because molecular weight of helium is 1. 8 grams of oxygen is 1 by 4 moles because molecular weight of oxygen is 32. So 8 by 32. So number of moles of 1 gram of hydrogen is 0.5, 0.25, 1 and 0.25. So among these four, which has the highest number of moles? 4 grams of helium, it's 1 mole. Therefore, helium exerts higher partial pressure. So the next one is a vessel containing two gas, hydrogen and oxygen at 1 atmosphere pressure, separated by a compartment. If the compartment is removed, what happens to the pressure? A vessel containing two gas, oxygen and hydrogen, at 1 atmosphere pressure. That means both the gases have the same pressure, 1 atmosphere and 1 atmosphere. If the compartment is removed, the pressure remains same. Assume, friends, assume it is a room. It is a room. In this room, the gas is there. If the pressure of the gas at this point and the pressure of the gas is this point, is same, 1 atmosphere. If this room is divided into two parts by using a cardboard separation, or if the room is divided into two boxes or two compartments by using a brick wall, then what will happen? Is there any change in the pressure of this room or that room? The pressure becomes same. Here also, the vessel containing two gas, hydrogen and oxygen, at 1 atmosphere, initially separated by a wall or partition. If the partition is removed, because the pressure of this gas is 1 atmosphere and the pressure of that gas is 1 atmosphere, so its volume will be the same. So it remains the same. Like that, one or more than options, 2 grams of hydrogen, 32 grams of oxygen are present in a mixture. The partial pressure of hydrogen is very simple, direct question. According to Dalton's law, I think there is a key mistake. Stage 2, question number 9, there is a key mistake. According to Dalton's law, total pressure is equal to P1 plus P2 plus P3 up to Pn. That's right. The total pressure of a gas mixture is equal to sum of the pressures of all the gases present in the mixture. It's right. Or, observe the second option. Total pressure of the gas mixture is equal to number of moles of first gas plus number of moles of second gas plus number of moles of third gas up to N into RT by V. It is also correct. Total pressure is equal to total mole number into RT by V. In the first one, I have given that formula. Or third one, the total pressure is equal to partial pressure of first gas. Partial pressure of first gas is nothing but N1 into RT by V. Partial pressure of second gas, P is equal to N2 into RT by V. Partial pressure of third gas, N3 into RT by V. Up to Nn into RT by V. So it is nothing but this one. In this, RT by V is the common factor. It gives N1 plus N2 plus N3. So the answer is, according to the Dalton's law, total pressure is equal to P1 plus P2 plus P3, so on. That's right. Our total pressure is equal to total number of moles of all the gases present in the mixture into RT by V. It's right. And the total pressure of the gas mixture is equal to N1 into RT by V plus N2 into RT by V, N3 into RT by V, so on. So all the above are correct. So options are 1, 2 and 3. 1, 2, 3 are correct. What is the given in the answer? Here is the desktop ఇక్కడ కనిపించట్లేదమ్మా. Okay. So for this, What option is given? Let us see. Ninth question, stage 2. Ninth question, stage 2. Answer is given as 1. Stage 2, ninth question, answer is given as 1. But not only the 1, 2, 3, and all these 3 are correct. Then 2 containers X and Y at 300 kelvins and 350 kelvins are with water vapor, pressure of 22 millimeters and 40 millimeters respectively. They are connected initially closely with the valve. Identify the correct statement. If the valve is open, the final pressure of each container is 31 millimeters. If the valve is open, the final pressure of each container is 40 millimeters. Mass of liquid water in X increases. Mass of liquid water in Y decreases. That is the understanding level question. X and Y, 2 containers. The first container is at the temperature of 300 kelvins and the second container is at the temperature of 350 kelvins. In both the containers, water vapor is present. In the first container, the vapor pressure is 22 millimeters and the second one, the vapor pressure is 40 millimeters. If the 2 containers are connected through a valve, if the valve is open, then what will happen among these 4? I will explain. There are 2 containers. A and B. In the A, in both some water vapor is given. The first vessel is at the temperature of 300 kelvins and the second one is at the temperature of 350 kelvins. In the first vessel, the vapor pressure is given as 22 millimeters. 22 millimeters and second one is 40 millimeters. The vapor pressure in the first container is 22 millimeters and the vapor pressure in the second one is 40 millimeters. If the 2 containers are connected through a valve, initially that valve is closed. Now these 2 containers are connected together by opening this valve. This valve is open. What will happen if the valve is open? These 2 are mixed together. So the first container contains water vapor at a temperature of 300 kelvins with a pressure of 22 millimeters. And the second container contains its same vapor pressure at 40 millimeters pressure and 350 kelvins. If the two containers are connected by opening the valve, these 2 are mixed together. Friends, you know that any gaseous compound that moves from high pressure to low pressure, here the pressure is 40 millimeters, here the pressure is 22 millimeters. If the valve is open, what will happen? The gases flow from high pressure area to low pressure area. Is it not? That's first one. Second one, here the temperature is 350, here the temperature is 300. If the temperature is more, then also it tends to occupy the more volume, because the volume is directly proportional to temperature according to Charles. Because if the temperature is more than that, it tends to this gas or the water vapor tend to occupy more volume. Therefore, by the effect of temperature, again this water vapor tend to display. Therefore, if these two containers with 22 millimeters pressure and 40 millimeters pressure and 300 kelvins and 350 kelvins, they are connected to the wall, then the more water vapor present in the B, that tend to flow into the A. As a result, more water vapor passes to the A. Therefore, the liquid water will increase in the A and the liquid water will decrease in the container B. Yes, let us see the options. Mass of the liquid water in X increases. We have taken A and B, here X and A. And the mass of the liquid water Y decreases. X is 300 millimeters and 300 kelvins, 22 millimeters. Y is at 350 kelvins and 40 millimeters. Yes, 22 millimeters. The liquid volume increases in X or A, and the liquid water, mass of liquid water decreases in container B or Y. Yes. This is somewhat a different question, that's advanced model. Yes, in the conference session, yes, all are given. In the 11th question, it is so easy. The total pressure of the gas which is collected through the water is 745. If the aqueous tension is 23.8, here I will explain a simple concept. Friends, you should know one thing. Some gases are collected through water. Remember the preparation of oxygen. When the oxygen is prepared by heating potassium chlorate and manganese oxide, it gives oxygen. That oxygen is collected through water. Therefore, if any gas is collected through water, then what will happen? Some of the water that mixed with the gas in the form of water vapor. Therefore, if the gas is collected over water, the gas will be mixed with some amount of water vapor. The pressure exerted by the water vapor is called as aqueous tension. The pressure exerted by the water vapor is called as aqueous tension. Now, it's again Dalton's law is applicable. The total pressure of a gas which is collected over water is equal to, that means the pressure of a gas, the pressure of gas means the pressure of dry gas. Yes, the pressure of a dry gas plus aqueous tension is equal to the pressure of wet gas. What do you mean by wet gas? The gas plus water vapor, that is called wet gas. So the pressure of wet gas is nothing but the pressure of dry gas plus the pressure exerted by the water vapor. The pressure exerted by the water vapor is called aqueous tension. Therefore, the pressure of a gas, that is dry gas plus aqueous tension, is equal to the pressure of wet gas. Therefore, the pressure of dry gas is equal to the pressure of the wet gas minus aqueous tension. What is aqueous tension? The pressure exerted by the water vapor at the temperature is called aqueous tension. It is a formula. It is the meaning of aqueous tension. It is the pressure of dry gas and it is the pressure of wet gas. Now, coming to the problem. 160 milliliters of a gas collected over water. A gas is collected over water at 25 degrees at a pressure of 745 millimeters. That means the pressure of wet gas is 745. If the aqueous tension at the 25 degrees centigrade is 23.8, అంటే the pressure of wet gas is 745 and the aqueous section is 23.8. So the pressure of wet gas is given as 740. The pressure of the wet gas is given as 745. 745. And the aqueous section is given as 23.8. So pressure of dry gas is equal, wet gas pressure is given, aqueous section is given. Therefore, you can calculate the pressure of dry gas. So it is the application of Dalton's law. It is nothing but Dalton's law. Pressure of dry gas plus pressure exerted by the water vapor is equal to the total pressure of the gas plus water vapor. That is called wet gas. As next one, 500 milliliters of gas A at 100 torrs and 100 milliliters of gas B at 800 torrs are placed in a 2 liters container. What is the final pressure? Already we discussed in the part 2. If two different volumes of gases at different pressures are mixed together, the pressure of the mixture is equal P1V1 plus P2V2 by total volume. Already we solved this problem. At constant temperature, 200 cc bulb containing nitrogen at 760 millimeters and 400 cc bulb containing oxide 750 pressure. The final pressure is the same. P1V1 plus P2V2 by total volume. Here the total volume is the two vessels are connected with each other. The two containers are connected with each other. If the two containers are connected with each other, then the final volume is V1 plus V2. Let us take that. If a box is there, open box is there, its volume is V1. Another box is there, its volume is V2. What will happen? If the box and if the box are connected through their open edges, then what will be the volume? V1 plus V2. So, if you observe this one, at constant temperature, the 200 cc bulb containing nitrogen at 720 millimeters pressure. So, the volume of the first bulb is 200 cc and 400 cc bulb containing oxygen 750. So, the volume of the second container is 450. Those are connected together. Then what will be the total volume? V1 plus V2. Therefore, the total pressure of the mixture is equal to P1V1 plus P2V2 by total volume. Total volume means here the two containers are connected with each other. That means the volume is V1 plus V2. Just solve it. It's also very easy. Only the difference is here the two bulbs are connected together. Therefore, if the two bulbs are connected together, the total volume is V1 plus V2. As in the passage, combination, the Tobias-Dalton's law. A is carbon monoxide, B is chlorine, C is fluorine, D is oxygen. The Dalton's law is applicable for which combination of gases? Friends, we should know that the Dalton's law is applicable only for the non-reacting gas mixtures. If the two gases are reacted with each other, then the partial Dalton's law is not applicable. The Dalton's law is applicable only for the non-reacting gas mixtures. The gas A is carbon monoxide, gas B is chlorine, gas C is fluorine, gas D is oxygen. If A and B are combined, A and B, carbon monoxide plus chlorine, is the Dalton's law is applicable for the mixture of carbon monoxide and chlorine, A and B? No, because chlorine reacts with carbon monoxide and it forms carbonyl chloride. What is the question? Carbon monoxide and chlorine. If carbon monoxide and chlorine are mixed in a flask, the carbon monoxide reacts with chlorine and it forms carbonyl chloride. So carbon monoxide and chlorine are reacting gas mixtures. The Dalton's law is not applicable for the reacting gas mixtures. Therefore, Dalton's law is not applicable for the A plus B and a carbon monoxide plus chlorine. Then second option, B and C. B is chlorine and C is fluorine. No reaction between chlorine and fluorine at room temperature. Therefore, the Dalton's law is applicable second option, B and C. And third option, B and D. B is chlorine, D is oxygen. No reaction between chlorine and oxygen under normal conditions. So Dalton's law is also applicable for the B and D combination, the third option. A and C. A is carbon monoxide, C is fluorine. Like chlorine, fluorine can also react with carbon monoxide. Therefore, carbon monoxide and fluorine are reacting gas mixtures. So the Dalton's law is not applicable for A and C. Therefore, the Dalton's law obeys second option and third option. I think there is a key mistake. What is the question number here? Question number 14. Question number 14. Only third option is given. But the correct answer is not only the third option, B and D, of course it is the correct option. B and C. B and C. No reaction between chlorine and fluorine under normal temperature. Therefore, both second and third options are correct. Then, the partial pressure of gases can be calculated by direct formula. You can recognize which formula is correct one. The law of partial volumes is also known as, friends, the law of partial volumes. The law of partial pressures is given by Dalton, which is called as Dalton's law of partial pressure. The law of partial volume, that is called Amigat's law. The total volume of a gas mixture at constant pressure and temperature is equal to the partial volumes of all the gases. Similarly to, instead of pressure, we use the volume. That is called Amigat's law. Here also there is key mistake. In the key, one option is given, it is wrong, the second option is correct. Like that, in the matching, you can answer any one. There are two matrix matching types are given. Even the integer type, same 2 grams of hydrogen, 64 grams of oxygen at exact a pressure of 3 atmospheres. Calculate the pressure of the partial pressure of XY gas, partial pressure of oxygen. Direct question. A mixture of non-reacting gas exerts a pressure of 5 atmospheres. If one gas occupied 40% by volume, what would be its pressure? The volume percentage, already we have solved this type of problem. A vessel containing equal weights of methane and oxygen, the partial pressure of oxygen is 1 by x. Calculate the x value. It's a normal problem. Like that, in the stage 1, stage 2, including advanced level, we discussed all the model. Please go through it. Try to solve each and every problem. Based on this discussion, you can answer all the questions. Try it. If you got any doubt, please contact me through WhatsApp only. Now, then I will give you the answer through WhatsApp. If necessary, I will call you. Yes, thank you.